Hello everyone and welcome to another video. So today I'd like to continue our discussion on vector integral calculus by taking a look at Green's theorem. So the first thing I think we can do is let's just take a look at the statement of the theorem and then just try to get a little bit of physical understanding of what it's really trying to describe. So let's look at this first sentence. It says that Green's theorem involves a region R, which is a closed bounded region, which has some boundary C, which is consisting of finitely many smooth curves and is positively oriented. Okay, so let's stop at that first sentence. I've drawn a picture to kind of get an idea of this. So again, we've got an XY plane, and in this plane, we've got a region R. And the region R, as you can imagine, it has some kind of boundary or some kind of perimeter. Let's call this perimeter C, okay? Now, we can see that C, it's made up of finitely many smooth curves. As you can see here, it doesn't have to be, just one continuous smooth line. It can be several disjoint lines as long as they're all smooth individually, right? Now, this other definition here of positively oriented, notice here that this curve C, we can have an orientation in the sense of either going counterclockwise or clockwise. So what positively oriented means is that if you were to walk along this boundary C in a specific direction, the region R is always going to be to your left. So again, I've stolen my daughter's little stuffed animal here, and you can imagine that this little stuffed animal is walking along the curve C, and the direction which is positively oriented means that they're walking in the direction so that the region R is always on the left-hand side of the person walking along this curve. So as you can see here, I've drawn arrows to denote the positively oriented direction. Okay, so if we're okay with that, I think that's the first sentence. Let's take a look at the next sentence here, okay? So with Green's theorem, it says, let's say that we've got two potential functions, which are called f1 and f2, and this function f1 and f2, they're defined everywhere in this region R at any given xy location, right? So it's just some continuous function, and more importantly, it has continuous partial derivatives in the sense that f1 can be taken, you can take a partial derivative with respect to y, and f2 you can take a partial derivative with respect to x. And you can do that everywhere on the region. So again, just think of it as some arbitrary function. We'll take a closer look at what that physically means a little bit later. But that's the basic setup, okay? Now, if that is true, then what Green's theorem states is that you can basically look at a closed curved line integral here of the quantity f1 dx plus f2 dy, and that is equal to a equivalent double integral over that region R of this sort of weird mixed quantity of the partial derivatives, okay? So that's the general setup of Green's theorem, and at the end of the day, what it's really talking about is relating a line integral over this curve C to a double integral over the region R. And again, remember, we had dedicated videos talking about line integrals and double integrals. So now here in this discussion, we want to look at how they could be potentially related in this particular special case. So a couple of comments that might be worth stating right here to help with our understanding. Let's make a comment number one, how about? And this is related to work. So if you remember in our discussion of line integrals, if we consider, let's go ahead and think about a vector function f, which at any xy location, it basically defines a vector, right? So the picture that goes along with this is that maybe you've got a vector field, at every location, it might be doing something different. Who knows what this is doing? I'm just going to arbitrarily draw it, right? But you've got some vector function f, like that, right? Now, we can think about this is, what if we take these functions f1 and f2 and we consider f1 to be the x component of the vector field and f2 to be the y component of the vector field, like this, right? So now what we've got is these f1 and f2s, you can think about them as being a vector function defined over this region R, okay? So if you remember in our discussion of line integrals, what we saw is that the work that's done by this vector field, if you were to try to move a particle along this curve C through this vector field or vector function f, the work done by that, it's basically going to be what? It's going to be the integral over the curve of the force field function, evaluated at any location, times dr, right? Where dr was your infinitesimal distance along the path, right? So in this case, C that we're looking at is a closed integral. So sometimes, you might see this symbol here to denote that this is a closed curve. So again, closed curve, right? And now if you look at the right side of Green's theorem, right, what is this really doing? It's looking at the x component of the force field dotted with the x displacement. So this is almost like the work due to x plus the y component of the force field times the y displacement. So the y component of work. So really, this over here is really the work, right? So what's interesting is I guess you could almost put an equal sign right here, right? And we see that really the right-hand side of Green's theorem is really measuring the work done by this vector field F over the curve C, okay? So the nice thing about this, the first comment we see off the back is actually if you're you know, like an engineer and you want to kind of look at physical interpretations of why Green's theorem is maybe helpful, we see that it's allowing us to have an alternate way to calculate the work here. Instead of doing a line integral like we did earlier, you could just do a double integral over the region in this particular case, right? Okay, so that's the first comment. Number one is you can see that in this context, we can kind of think about this in the back of our mind as looking at work, right? How about let's look at another comment while we're talking about the work, right? Let's look about this as how this might be related to the curl. So you remember we actually had another dedicated video talking about the curl operator. So we saw that the curl operator was a vector operator on a vector field, and really it actually had a term that looked really similar to this right here. In fact, if you rewatch our video on the curl, you'll see that you can rewrite this term over here as basically you can have double integral over the region. So instead of that mixed partial, you can basically say this is the curl of the vector function f, like this. And if you remember, this is a 3-element vector. So I actually only want the third component of this vector component. So I'm going to dot this with the unit vector in the third dimension, or the k unit vector, right? So this dotted with times dx dy. So this term right here that maybe I'll highlight in a different color, I'll just underline right here. If you work this math out, this is an alternative way to express this over here. And again, let me underline it in orange, okay? So again, it's just an alternate way that you'll see it. Most of the time you will see Green's theorem stated like this, but you can basically interpret the left side of it as curl if you want. Curl dotted with a 0, 0, 1 vector, right? It's just another way you can maybe write this, okay? And then lastly, maybe if you think about this long enough, really this is a double integral over just some region r times dA. So that assumes Cartesian coordinates. So the last thing that maybe we'll make a comment on is, you know, you could write this in more in generalized coordinates if you wanted to, because really that's just a double integral, right? So in other words, you could potentially write this left side here, right? It's basically it's this same thing, right? It's curl of f dotted with k, right? And then this thing, this is really like a dA, right? So this might be helpful because this might allow you to maybe convert this from Cartesian to say polar coordinates, and then all that's going to require is a reformulation of dA into basically an r dr d theta. I think, again, we talked about that in our double integral discussion. But again, think about this as just a double integral. You can do it in Cartesian. You can do it in polar coordinates, however you like, right? So again, Green's theorem is basically saying this, right, is sort of a more generalized left-hand side is equal to, again, what we've got over on the right side is, again, you could also think about this as the right side. It's really just a line integral of the work as we discussed, right? So it's f dotted with dr. So again, here's maybe another way you could think about it if you want, but at the end of the day, it's really talking about a double integral over the region R is somehow related to a line integral over the closed curve C. You can either think about it in general form here, or the more common kind of Cartesian expression that you'll see in, you know, like Wikipedia or other, you know, common math texts will maybe state it like this, but this is what we're talking about at the end of the day, right? Okay, so tell you what, why don't we go ahead and let's look at an example of how we can use Green's theorem to calculate the work. All right, so let's look at an example. Let's say you've got a vector field f which looks like this, okay? And again, we're going to consider the x component of the vector field to be that function f1 in Green's theorem, and the y component of the vector function to be the f2 function in Green's theorem, okay? So we've got this vector field or vector function defined, and we want to understand what is the work done by this vector field to move a particle along this curve C, which is sort of this triangular shape here, and I guess I forgot to mention the limits here. This is 1 and 1. So something like this. It's like this unit triangle, so to speak, okay? So we want to understand what's the work needed to do this. And again, it might be helpful to plot this vector field just so we get a rough intuitive feel of what this looks like. And again, I'm not going to try to sketch this instead. I'll show you a screenshot here of, I did this in Mathematica, so you can kind of see that the vector field is a little bit complicated. So in some parts it's doing positive work, some parts it's doing negative work, you know, et cetera, et cetera. But long story short, we want to compute the total work it takes to go from here to this corner, up to that corner, and then back down to the origin. So basically to make a complete circle, okay? So that's what we're interested in doing, okay? So one way we could do this is let's go about this the sort of quote-unquote naive way, and let's just go ahead and compute 3 separate line integrals, right? Because it's just like we did earlier. So because this is something of a bit of a refresher, we talked about line integrals already, I'm going to walk through this a little bit more quickly. So what we're going to do is we're going to break that curve C into 3 separate curves. So C1 is going to be this lower curve down here. This is the horizontal part. Let's call that C1. C2 is this other part, which again, if you look at these parameterizations, you'll see that this is basically the parameterization where x is 1 minus t, y is t, and if you let t run between 0 and -1, what that ends up being is this diagonal portion going in this direction. And again, we got to be very careful on the orientation. We want to make sure that these curves are positively oriented, right? Okay, and then lastly, we're going to have C3 be this sort of downward vertical component over here. And again, you can see here's an appropriate parameterization that is going to get you the appropriate orientation, okay? So we've got these curves C1, C2, C3, and then what we can do is we can just use the normal property of line integrals, and we can say we can take an entire line integral over this curve C and break it up into 3 separate individual integrals. And again, be careful here with the notation, right? Remember, I drew a little circle here to denote that the left-hand side is a closed integral in the sense that this C starts and ends at the same location. But these individual integrals, they're not closed, right? They're just individual line integrals one at a time, right? Okay, so let's focus on this first term here. So this is this horizontal component going from the origin to the location 1, 0, okay? So let's look at this integral right here. So for that first integral, again, here's our parameterization R for that, that bottom horizontal part, right? It's just x is equal to t, y is equal to 0, and t runs from 0 to 1. And again, I think you'll see that this parameterization basically describes that bottom curve C1 very effectively, okay? So again, the next thing we're going to have to do for our line integrals is we're going to have to compute the derivative of this parameterization with respect to t, right? So I'm going to go ahead and do that. It's just basically take the derivative of this with respect to t, and you get 1, 0, okay? Great, that's super easy. The next thing we have to do is we would then have to evaluate the vector field along the curve or the parameterized curve down here, right? We just have to understand how is the vector field changing as you move along this curve, right? I don't care about it anywhere else. So I'm looking at the vector field only evaluated along this curve, whoops, R1, right? Okay, so all that means is you take the general vector field here, and I want to evaluate it along the curve R1. So in that case, R1 is when x is equal to t and y is equal to 0. So you plug that in, you just get this. You get t squared and t cubed, okay? That's what the vector field looks like along the curve. So now, again, from our line integral discussion and video earlier, we saw that, okay, in order to calculate this line integral, which is really telling me the work done by that vector field along the curve C1, is here's the mathematical definition, right? It's just the vector field dotted with sort of your infinitesimal displacement here. But practically the way we're going to compute this is we're going to go ahead and use the parameterized version where we're going to run t from 0 to 1. And here, this term is, again, this is the vector field along our location dotted with this part here is basically dr, right? We had to take a look at the tangent and dot it with the dt, right? So this is what we end up with. So I ran out of space, so let's go ahead and continue this work over here. So that side becomes, again, 0 to 1, and then f of r of t, that's, excuse me, r1. I guess I probably should have put 1s on these, right? Because we're looking at the first curve. Okay, so basically this term is this, so I need to put in this thing. It's t squared t cubed, right? It's just a 2 by 1 vector dotted with, what's our r prime, r1 prime? That is right up here, so dotted with 1, 0 dt. Great, and you look at that, that actually becomes pretty easy. This becomes, it's just what, t squared dt, 0 to 1. And again, if you go ahead and evaluate this, that is pretty simple at this point. I think you end up with 1/3, right? Okay, so that's the work done for this first curve. You can basically do the exact same thing for integral number 2. All you're gonna have to do is change some of these. So now this is now R2, is the parameterization is, what is this? Now this becomes 1 minus t, and y becomes t, and again t runs from 0 to 1. So now again I can calculate r2 prime, which is basically taking the derivative of r2 with respect to t. So what do we end up with? This is what, -1 and +1. Again, let me just double check to make sure that I've got this thing correct. Yep, okay, great. So now we're going to evaluate the vector field along R2. So I need to look at the vector field along R2. So here's the vector field, and now x and y are described by this parameterization, right? 1 minus t and t. And this term over here becomes, now, if you go ahead and plug that in, what did I do with it? Oh, okay, so this thing's a little bit more complicated, right? 1 minus t squared minus t, and then 1 minus t cubed minus t. Okay, and then blah, blah, blah. Again, you see, just keep updating all of this to now say 2's instead of 1's, right? Okay, and again, we end up with this term over here, and tell you what, I think this is a little bit of plug and chug at this point, but I guess we can do a few more terms just for completeness. So we want this term, which is this here, right? This is the vector field along the curve, so this is 1 minus t squared minus t, and then 1 minus t cubed minus t. Okay, this dotted with, what do we have here? -1 and 1. And then at the end of the day, this now becomes, I don't know if I actually wrote out that term. Sorry, I don't have the integrand. Oh, sorry, this is dt. But I have the overall result. So tell you what, let's just write down the overall result. This thing becomes -1/12. So actually, along the diagonal, it looks like the vector field was overall opposing the motion rather than going with the motion. Okay, so again, you do this for R1, R2, and then you can also do it again for R3. Let me just see what I ended up with for R3. So the integral over R3, curve 3 of f dotted with dr, I think I got that to be 1/2. Okay, so overall you add up 1/2 plus -1/12, and what was the other one? 1/3, and I think we end up with the overall answer. Where do we have that? I don't know if I even have a spot here. Well, here, this is the work. So the total work we end up with is, I got 3/4. Okay, so that's one way we could go about doing this, is by basically just brute forcing it and computing the work. So now, how about, can we apply Green's theorem to see if we get the same answer? So tell you what, give me a second to erase some of this, and we'll do the double integral next. All right, so now let's use Green's theorem to get this same amount of work. So recall, Green's theorem basically said that this line integral was basically the equivalent of this double integral of this sort of weird mixed term of partial derivatives over the equivalent region. So the first thing we should do is, let's go ahead and calculate this integrand right here. So again, this integrand is nothing more than taking the partial derivative of x of f2, right? So again, you got to remember, this is sort of a little bit mixed up. You take the y component of the vector field, you take its x derivative, and then you subtract it from the x component of the vector field and its y derivative, right? So again, you do this, and this is what you end up with. So this double integral actually becomes this. And you can see right off the bat, this is one of the things that's nice about Green's theorem, is that we've basically, sort of quote unquote taken a derivative. So now we have an integrand, which is a lot easier, right? Because this is, derivatives tend to knock out terms or simplify the expression. So usually this is going to be easier to integrate than this thing over here, okay? Again, of course, the trade-off I think that we pay, what's the phrase? I had a professor that always said there's no free lunch, right? So we have an easier integrand, but now instead of a single integral, we're now dealing with a double integral here. But again, something to think about. You can easily see the integrand's easier, but now we're forced to deal with a double integral. So how are we going to deal with this double integral? Again, we had a good dedicated video discussing double integrals and how we can handle these. Let's go ahead and maybe treat this first as let's treat this as a type 1 region and integrate with respect to y first in this direction, okay? So if that's the case and we're going to choose this as a type 1 region, I think we can see that the bottom limit of integration down here, this surface or this curve, right, is basically y equals 0, and the upper part that we're integrating to is basically y equals negative x plus 1. I think everyone would agree, right? So the y limit is going to go from y equals 0 to y equals negative x plus 1. So tell you what, let's actually flip the order of integration since we're doing a type 1 region, and we are going to rewrite this guy as this. I want actually dy dx, and again, we've got the integrand, same integrand. But again, I'm going to draw parentheses just to kind of keep myself sane, and I can do one of them at a time. So let's do this inner integral with respect to dy, and we saw that since it's a type 1, we're saying y goes from 0 to negative x plus 1, right? That's the y limits. And then the x limits of integration we can see go from 0 to 1, right? So then here we go. So we set that up. So at this point, it's a turn the crank because this is just two single integrals, but you got to do them successively one after the other. I'm going to skip you the boring watching me do this on the board because this is pretty simple. Just run over to Mathematica, have it, do this integration, and la-di-da, you end up with 3/4. So it's the exact same number that we got earlier. So this shows that it works here. And again, you can get the exact same result if you treated this as a type 2 and went the other direction, okay? So again, this is maybe just the single instance showing how Green's theorem works. And you can see that in my mind, I think the double integral is easier and faster in this particular situation than doing the line integral. All right, so we saw how Green's theorem could be used to calculate the work of a force field moving a particle through a curve C. What else could it be used for? How about, can we use it to calculate the area of this region R, right? So let's say someone dropped into your lap this region R, it's something funny looking, and they ask you for the area, right? Well, if you remember from our discussion of double integrals, right, the area of this, it's just the double integral of this. The integrand in this case is just unity, or 1, right? Because basically, this gives you the volume of a surface of height 1 over this region R, which is basically the same thing as the area since the height is 1, right? So this is the way you can calculate the area, right? It's just do a double integral. Now, the problem is, right, I don't know if you want to call this a type 1 or type 2 or find out some other way to do this because this is not a simple region where it's this integral is going to be difficult to compute due to the funny geometry of this problem R, right? So this is not the easiest thing in the world to go about doing. Now, how can we bring Green's theorem to bear? Let's say, what if we're able to just cook up some functions f1 and f2 such that by the time you take the x derivative of f2 and subtract the y derivative of f1, you get unity, right? You get 1. Okay, what does Green's theorem say in this case? Remember, here's the general case of Green's theorem, right? This works all the time, right? But now what we've said is that this thing in here, this is just 1. So the left-hand side of this thing is just r of 1 times dx dy, right? Look at that. That is the same thing as the area. So the left-hand side of this is basically area of the region R, right? And now Green's theorem is telling us in this case, the other way that you can get this area is instead of doing that double integral, you can actually do a line integral of this funny quantity right here, right? Of this weird vector field. The work here is basically telling us the area in this case if we can cook up this funny vector field f1 and f2. So the only requirement is that this has to happen, right? By the time you take these partials, you get, and then subtract them, you get 1. So some popular choices of this are, you can easily use here, let's make a table. There's many different ways that you can go about this and it will work. So for example, if you choose an f1 of 0 and an f2 of just plain old x, you know, by the time you take this derivative, yeah, it comes out to 1. And again, this is not unique. You could choose, how about f1 of negative y and 0? That works. You could choose something like a negative y over 2 and x over 2. I think all that works. So again, there's no unique combination. Let's just use this maybe as an example. So let's look at an example of applying this to calculate the area of an object, but we're going to calculate the area using a line integral instead of a double integral. All right, so let's take a look at an example of trying to calculate the area of this ellipse. So this is an ellipse with a semi-major axis of A and a semi-minor axis of B. So again, I'm sure you can look this equation up for the area of this ellipse anywhere, like on Google, but let's just derive it via Green's theorem and see if we get the same answer. Okay, so again, refresh your memory that basically this ellipse is basically defined by all the points x, y such that this is true, right? The other way that we could look at this ellipse is we could look at parameterizing this ellipse, and namely the curve C, using this, right? All the x locations are a cosine t, y is b sine t, and t runs between 0 and 2 pi. So this is another way to parameterize this curve C, which is the outside of the ellipse. Now, since we want to go ahead and calculate the area via Green's theorem, we're going to choose this pair of f1 and f2 for our vector field to make sure that we get the proper basically mixing of the partial derivatives to get unity for the integrand. Okay, so we're going to choose that. So now at this point, it's basically just going ahead and applying Green's theorem. So Green's theorem says that, okay, instead of doing that double integral, we are now going to go ahead and get the area of R by doing this single line integral around the curve C of these two quantities. Okay, so since we know what f1 and f2 are, just plug them in and we end up with, well, this is all we're left with. It's just x dy, right? It's just this term right here, because this is gone, because f1 is 0, right? So this becomes simpler. And now, with this parameterization of the curve C in mind, we can actually substitute that in right now. So let's take a look and see what this integral becomes. So this is now, the curve goes now from 0 to 2, no, actually, let's leave it as C for now, right? Let's leave limits of integration C, and x is just a cosine of t dy, okay? Now, what we could have done is we could have gone back and done the whole normal line integral, but let's just go ahead and, since this is so simple, let's just go ahead and make a note here that dy, what is dy? Dy, well, we can look at what y is. We said y is right here, right? Y is b sine t, right? So I think everyone would agree that dy, right, is just nothing more than b cosine t dt, right? If you just take the kind of derivative of this. So great, let's substitute this in for dy so we can change the limits of integration from dy to dt. So this now becomes basically integral of a cosine of t, and then I got to substitute all this junk in. It's b cosine of t dt, and now my limits of integration are from dt from 0 to 2 pi, right? So at this point, I think you can basically pull a and b out, so we end up with integral, AB times the integral from 0 to 2 pi of nothing more than just cosine of t squared dt, okay? So again, you go run over and you evaluate this. If you're interested, I've got a little trick in my notes to talk about how to evaluate this integral analytically. But long story short, this whole thing turns into just pi. So we end up with just pi AB as the answer, and that is apparently, in this case, the area of this ellipse of region R, okay? So, and again, that lines up with the typical definition of the area of the ellipse. We just got it from analytical principles using Green's theorem, so it looks like it checks out here. All right, so there you have it. That's a pretty good discussion, I think, for Green's theorem. So just to summarize, we saw that what Green's theorem is really doing is it's allowing us to relate a line integral over a curved surface C to basically a double integral over that equivalent region R. So right here, I think this is one of the places where we see, one of the reasons why you might want to use Green's theorem is that if you have a vector field F, sometimes this line integral might be a little bit complicated because, it's a line integral and this f could be somewhat tricky. So one benefit of using Green's theorem is that Green's theorem is effectively kind of taking a derivative of the vector function f, right? Because you're now working with the curl of f, right? We talked about how this is sort of the general formulation of Green's theorem. So this is usually much simpler than f by itself. So Hopefully the integrand is more easily handled over here on the left side where you're doing a double integral. Of course, like we said, no free lunch. The price you pay for having a simpler integrand is now, instead of a single integral, you are now doing a double integral. But in general, I think usually the left-hand side is easier to calculate. So the other thing that's interesting about Green's theorem is that we are going to see later in a future video that Green's theorem is actually a specialized version of a more generalized theorem known as Stokes' theorem. So really, what we're going to want to investigate in one of our future videos is Stokes' theorem, because that is going to sort of supersede some of this, or at least be applied in a little bit more general cases. That being said, Green's theorem is still pretty popular, and we saw there's many applications like calculating the work, calculating the area, and simplifying integrals. So it's pretty versatile. So with that being said, I think this is a great spot to leave it. I hope you enjoyed the video, and if so, I also hope you'll consider subscribing to the channel. If you just scroll a little ways down and click on that subscribe button, it really does help me continue making these videos. And remember, the new videos come out every Monday, so I hope I'll catch you on one of these future discussions, and we can all learn something new together. So until then, I think I'll sign off. Talk to you later. Bye.